Yeah, so this is about E203 network theory, and we have studied something called magnitude response, right? In magnitude response, what we have learned, if such kind of transfer function is given to you, if omega is very much lesser than a, what is going to happen? Yeah, the last gentleman. Yeah, the word. Yes, yes, yes. So if omega is much lesser than a, then what will be the magnitude of this transfer function? Yes, yes, you. Magnitude. So your neighbor can help you. If you want. Yeah. Yes. Hmm? So transfer function in g omega we can write down like this. The magnitude will be omega square plus a square, right? Decibel we can write down in minus 20 log omega square plus a square is to minus 1 by 2. So if omega is much lesser than a, then what are you going to see here? What 1 by a? Minus minus 20 log a, right? Sorry. Right, this is correct one, right? So this is just a what you have learned. So minus 20 log omega, that will be if it is much higher than a, and other things we learn, right? But we also learn that when we are drawing this, so at frequency of a, and when it is much lower than a frequency, then let's assume that this is minus 20 log a, and thereafter it is decreasing by minus 20 dB per decade because it's only one pole, right? Or it's equivalent to minus 6 dB per octave. Yeah, all good, all fine, right? So one more thing we have learned, right? This decrement will be some minus 3 times minus 3 times r times dB, right? In this case, okay. In this case, it will be a, right? So we talk about all these things and we studied it, but these are the curves which are the real curves, or these are the smoother one. It looks like this one. Hmm? No, no, minus 20 dB per decade. This is the correct one. It depends on a. It might be plus or depend on whatever the value of a. Okay. If you like, okay. Hmm? Yeah. Right. Huh. That's correct. Right. So this is the thing we learned, but let's summarize what we have learned, because I want to make a body plot, and what he says that do not do all these things, just draw the lines which are the asymptotic lines. So at a, till a you will have the magnitude of minus 20 log a, and thereafter there is sharp slope which is minus 20 dB per decade. This is what you are going to observe. So this is what Bode told. We are not going to make something minus 3 dB down or something like that, right? We are going to draw the sharp lines. So let's summarize what exactly Bode plot says. So Bode plot is a frequency response. It's also equal to AC response. which we already talked about in the first class itself. The plot is composed of the magnitude as well as the phase plot. Today we are going to study only the magnitude plot on paper, not the phase plot. The phase plot is very easy compared to magnitude one. So let's discuss that. X-axis is either in a radian per second or in hertz. So whichever you like, angular frequency or the normal frequency, that one you can choose and you can use it. X-axis is generally in log scale. That's why we are using the semi-log paper. One side is log and one side is linear. So that is how we are going to do. The magnitude will be measured in terms of dB. It's in decibel. You know what is decibel, which is 20 log times some number. If this is ratio, it's dB. If this is not ratio, if it is voltage, then it will become dBV if it is voltage. The phase is measured in degree and used to determine only one thing, stability. Degree like 45 degree, 60 degree, right? Anything wrong? X-axis. It's copied. Right. So, oh, both are x-axis. Yeah, that's correct. What's the problem? Both are correct. What's the problem? I'm redefining it. X-axis has a scale of radian per second or maybe hertz, right? And we are going to use it in log scale. X-axis will be in log scale. So the paper which you have right now, it's in log scale. Right? How to read it, I'm going to teach you that also. So these are the things for Bode plot. Let's redefine all the stability measuring factors, such as small signal gain. Everybody knows what is a small signal gain. Small signal gain, DC gain, AC gain, or differential gain, all are same, all are synonyms. Any one of the name you are calling, all are like same. So if I am drawing such kind of Bode plot, means this red colored highlighted area is small signal gain, it's AC gain, it's differential gain, it might be low frequency gain, right? All are synonyms. So any one of the name you can call it. Okay, the next thing is unity gain bandwidth. So unity gain name suggests that when the gain is unity, the gain is unity when axis is 0 dB, right? 0 dB is nothing but when VO equal to Vin. So it's 0 dB. Means your gain is unity. That particular point is going to call UGVW. So this is the name we electronics people say. If you are with some mechanical faculty or control faculty, they are not going to call this name, but there is another name which is called gain crossover frequency. By the way, again, these two names are same, right? Different two people are talking in different language, but it's same thing, right? Third thing is phase margin and gain margin. Okay, so phase margin is the one. Okay, let's define it afterwards. Okay, when we are going to make the phase plot. But before that, let's look at this. And you have to tell me where are the locations of poles and zeros and type and order of the system. Very quickly, can you tell me?
Order is
Okay, so somebody told order. Order is somebody told two. Four. Okay, then it's correct. What about the type of the system? Two. So this is on the basis of how many integrators are there in the system, right? Right. So there are two integrators. So that decides the kind of PI controller in your system. So how many zeros are there, by the way?
two.
Minus 0.5 and minus 1.5. How many poles? Four. 0, 0, minus 1 and minus 3. Okay. And what is the small signal gain or low frequency gain, AC gain? Hmm? This is just revision what you have done, right? No problem till now. Type is 2. No, no, if it is cancelled, then we will not count it. No, right? There is no pole 0 infinity, right? Right now all the poles and zeros are poles are infinity, right? You see, in that case all the system look, two zeros, two poles are at origin, right? So which kind of system you are talking about when it's infinity? Yeah, so tell me the transfer function. This will only happen here. Yes, yes. If it is happening, then it's already very far, right? You cannot draw uh, in your semi-log paper. Such system will happen. If you want to see that, I can show you in analog circuit designing course. If you want to study that, I can show you that, but it's impossible to see it here, right? Okay, if all good, then there is no doubt, right? All are expert of evaluating such things. Okay, now yeah, so it's unstable system, so that is what I'm saying. That is not going to happen in your course. We are not studying any unstable system, or we are not making any unstable system to towards stable system. We are studying, or we are analyzing all the system which are stable. So that's out of the scope of this course. But if you want to study that, yes, of course it will be part of next course. Hmm. Four. Yeah, 0 is 0, but because of these two zeros the slope will change of your magnitude response. Instead of minus 20 dB it will be minus 40, right? So look, so if you are listening, let's say Radio Mirchi, which kind of plot is important for you, this one or this one? Red one. Why? because because you want to listen only one frequency, not so many frequencies which are disturbing each other, right? So if you want such kind of thing, you need to have the higher order of the system, right? Here you might have minus 20 and band pass, but here you need higher order, right? So it creates lots of difference. Okay, now there are some useful informations when we are drawing Bode plot. So if you have one single pole frequency, that is going to contribute minus 20 dB per decade. I'm not writing in octave now, right? So you should understand it's minus 60 dB per octave uh, of its equivalent. Single zero frequency is going to contribute plus 20 dB per decade, right? You can write down, maybe it will be useful. If there are multiple poles and zeros, so n times plus or minus 20 dB per decade of the slope. We got all this derivation, right? How you got this? The slope is calculated according to the previous slope calculation also. This was the question Divanshu asked last time, that one pole was giving me minus 20 and other was 0 which was contributing plus 20, and you are asking why it's becoming 0, because it's minus 20 plus 20 is going to be 0, so it takes care of the previous slope as well, right? Now the magnitude plot looks like this one. you may have 10 lines like this. If the first one, if you define it as 0.1, the next will be 1, next will be 10, next will be 100, because it's 10 base log scale, right, which has 10 base. The next thing which you are reading, the bigger line, if this is 0.1, then this will be 0.2, this will be 0.3, 0.4, 0.5, 0.6, and so on, 0.9, and then 1. When you are reading the next box, then this line will indicate what, 1.1, 1.2 or something, or something, 2. If you are reading 2, then it's the correct answer. 2, 3, 4, 5, 6, 7, 8, 9, right? And similarly here, you will read 20, 30, 40, 50, 60, and here 200, 300, 400, right? That's how this frequency is increasing. Yes, double is octave. Yes, it's octave. 0.2 to 0.4 is octave. Hmm? It's a Latin word. Octave is equal to double, right? Now, let's assume that when you are starting the Bode plot, it has only this transfer function, or you are saying this transfer function, k by s, right? Where k is the small signal gain, and just you have this transfer function, k by s. Then what you need to do? You need to go to 20 log k, okay, as you like the plus symbol. I forgot your name. What's your name? Manas. So Manas, you like plus, so I'm keeping plus 20 log k, right? It's same depending on value of k. So 20 log k, I'm here. This is 1 point, and as this is pole at origin, it's going to be contribute minus 20 dB per decade. That's the slope. So whatever the value is here, I'll go down by 20. I'll go down by 20, and I'll go 1 decade ahead. Means if this is 0.1, I'll go to 1, right? I'll keep these 2 points. Using scale, I'll make a line. That's the magnitude response of k by s, right? So this is I'm drawing just for one component. Afterwards, we will collect all together. Let's assume that you have a situation where instead of k by s, you are going to have k by s plus x. That is the transfer function given to you. Then you have to go to 20 log k, this point. You have to draw the line which is 0 dB right now, and you have to reach the value of x. X is the frequency. By the way, I made a mistake. It's log k by x. In this case, it will be log k by x, because we have to write down in terms of, right? So I have to write down in terms of tau s plus 1, if you remember, right? So afterwards, we are going to make another minus 20 dB per decade slope from the frequency of x. So from this point, I'll go down by minus 20. I'll go ahead 1 decade. I'll find out one more point. These 2 points, I'm going to make a line. That will give me minus 20 dB per decade. Are you following this, or is it going fast? Okay. Okay, so till now this is not a problem. The problem happens when there is a differentiator which is coming first, means k times s. So just for like what I follow, that is what I am showing you. There are many books, they are following in a different way. If you are following like Nagaraj Gopal, then it's a different way. If you are following the real book, which I like, Ogata, it's not required to read right now. It's control book. Okay, it's not required to read now. Okay, if you are studying control, then your professor must be teaching you that. So I'm following that book for drawing all this. So what you have to do, you have to go to the frequency of 1 by k. So if you are having the transfer function which looks like this one, then it's equal to 20 log k plus 20 log omega. Do you agree with me? This one, right? When I'm writing this, I want to find out what is happening at the 0 dB of value. When this transfer function becomes 0, means at this line 0 dB, what is going to happen here? So that is only happen when it's minus 20 log k, sorry, 20 log omega is equal to minus 20 log k, or this is happening at omega equal to 1 by k. That is what I am drawing here. At 1 by k it's 0. Let's keep that point, and I know that my pole is going to contribute plus 20 dB per decade. So from here I am going to draw the 20 dB per decade. So from this point I am going up by 20. I'll keep that point. From that point I am going one decade down, sorry, another side, right side, and I'll draw the line which is going to give me plus 20 dB per decade. Yeah, all good, all fine. Then okay, one more is similar to k divided by s plus x. You may have k times s plus x, means k times x. So you have to go to 20 log k times x. You have to draw the 0 dB line. You have to go till x value of frequency, and from there you have to draw plus 20 dB per decade. Yes. What is the name of you? Khyati. Okay. So this will give you the complete plot. Are you following this till now? Right. If it is k by s, you have to go to plus 20 log k, and there after you have to draw minus 20 dB per decade. If it is k times x, then you have to go to 1 by k, and you have to draw plus 20 dB per decade. If it is starting from somewhere else, then you have to draw the 0 dB and then go upside or downside. This is only going to happen when the system is type 0. Okay, this will only happen when the system is type 0, otherwise this will not happen. Okay, let's look at this. So now you have to draw the magnitude response of the system. You have to draw the magnitude response of the system in your Bode plot or semi-log paper. I'm going to help you. My TS will also help you. So the transfer function is s plus 1 and s plus 3. Now you can take help from my TS. Vivek, you can sit inside some of the students, and you can also sit somewhere inside this group of students, right? So that everybody will understand what is going on, right? And it's not a group activity, okay? So do not have just one semi-log paper and like others are looking at that, right? So everybody has to do this. So our strategy will be, so when this is the system is given to you, our strategy is you are going to write down all the poles and zeros. Let's write down poles and zeros. So poles are 0, 0, minus 1, minus 3, and minus point, minus 1.5. Right? When you are going to find out these poles and zeros, you should not start drawing Bode plot, but you have to order them. Like first is, there are first two are zeros. Can you see? These two are the poles, two poles. Thereafter, there is a zero which is at minus 0.5. Thereafter, there is a pole which is at minus 1. Thereafter, there is a pole which is at minus 1.5, and there is a 0 at minus 3. Yeah. Hmm? Is there any mistake? It's reverse. Right? So we we know that whenever there is a single pole, it's going to contribute how much value of slope? Minus 20 dB per decade, right? For two zeros, minus 40 dB per decade. So just write down somewhere. So let's make this table where you have frequency, value, and slope, right? Something like this. Now there is a 0. So what do you think about the slope? Plus 20. But if you remember, there is a statement I have written somewhere. The slope is calculated according to the previous slope calculation. So previous slope was minus 40. So you have to take care of minus 40, the previous, plus new slope. Okay, let's pick it with the green. So new slope is plus 20 dB per decade. So effectively it's minus 20 dB per decade. Right? Now, what do you think about this pole? Minus 20 minus plus 20 minus 20. So this pole is going to contribute minus 20, but it will remember the previous minus 20 also, right? So it has to take care of the previous minus 20. So it's effectively minus 40 dB per decade. Is there any undo? Yes. What about this 0? Plus or minus? Plus 20. So this is going to give you minus 20 dB per decade. This pole minus 20 will give you minus 40 dB per decade. Yes. Is there any problem in calculating this slope at a given frequency? If no problem, then I'll draw the magnitude plot. You also have to draw it in your log paper. So from where do you want to start your like first point? So there are various points are given. So first box, what do you want to take? Hmm? Yeah, you can take point 1, point 0.01 is also fine. Anything is fine, which will cover from this point to this point. From this point to this point, like the maximum point, minimum to maximum, will cover all the frequencies which is given in your transfer function, right? That is what you need to do. So you can start from point 1, no problem. You can keep point 1. So I agree with uh, Manas. So point 1, then next point will be 1, then next point will be 10, right? So I can draw my magnitude response in these two boxes without having any problem, right? Hmm? Oh, when we are drawing this, the frequencies are at the positive end only. Okay, good question. Yeah, in magnitude plot, we are drawing everything in positive side. So these frequencies, because in reality, this minus omega will not happen. Hmm? No, there is nothing like negative frequency right now. When we are drawing the magnitude plot in dB, it's always positive side, and we assume that this side it's a mirror image. If I am drawing this, means that this side it's exactly like this. Both the cases it will be at the positive side. It will be at the positive side. We are drawing only when it's positive, not negative. This is going to happen when uh, we are going to draw with the root locus. I'm going to tease that also afterwards. So if it is there, then there is an impact. Right now for stability, minus frequencies are not required. So now,
Sir, in case like there is a positive pole or positive zero along with the negative pole.
yeah, so still they are in this side only, positive side. Positive, yeah, everything will be positive, right? Positive side. Okay. Similarly, so minimum is minus 20, minus 40. So let's make one box equal to plus 20, right? One box on y-axis, which is linear scale, by the way. Right? So you have to choose some place where you are going to have the 0 dB line. Okay. Right now scale is not required, but yeah, just marking these values. Till now, all good or no? Along with these poles and zeros, you have to tell me the value of k also. What is value of k? 0.25. Okay, 0.25. So how much in dB, by the way? Somebody tell me without calculator, please. Okay, let's go this way. If it is half, how much? Half is equal to how much dB?
1.2.
No, no. Half is equal to 6 dB, by the way. Sorry, minus 6 dB.
12,
Hmm?
12, sorry, 12.
Okay, so it's equal to minus 12 dB. Yeah? No? Half is equal to minus 6 dB. So half of half will give you minus 12 dB. Right? Okay. So I'm going to start from minus 12 dB. So this is available gain to me. Now tell me, what next I need to do? I need to find out what kind of system it is. So it is following the first root follows this thing, k by s square. The first thing which I am saying. So I taught you following things. Whenever you are going to start, you may have k by s, then k by s plus x, k times s, or maybe k times s plus x, right? So this system starts with k divided by s square. Yeah, this is the first thing because this is at starting at the origin, right? So this particular system is going to contribute minus 40 dB per decade. This is what I want to draw. So where I need to go? I need to go to 20 log k point. 20 log k point is available at this point, right? 20 log k is here because that is equal to minus 12 dB, right? So minus, now it's, even if it is plus 20 log, still it's at minus, right? So it's depending on what value of k is there. So I'm here minus 12 dB. So you mark minus 12 dB in your uh, graph paper. This is one point. I need to draw minus 40 dB per decade. Now look at this, not minus 20, but it's minus 40 dB per decade. So you need to go down by minus 40. So around minus 52 dB and one decade ahead. Yeah. So you got this point and this point. Please draw the line which is passing through these 2 points. If you are getting any difficulty, please ask my TAs. They will help you, sure. Right? Hmm. Gaurav, please ask me any question is there. I'm drawing minus 40 because there are two poles, not one pole. There are two poles. I took like difficult system at the beginning itself, maybe. Right? Yeah. Mahima, are you following? Okay, your friend is not here, Nikita. Yeah. So, are you following this till now? Okay. Is there anybody who could not follow this? Nakul? If you're getting any difficulty, you can ask my TAs. They are expert to help you for sure. Or if you want, I can come to your desk also. Rishabh, fine. Okay. So considering everyone's like positive response, Kathy, all good. Kathy, okay. If you agree with this one, this plot is only valid till zero point 0.5. So you may see like 0.2, 0.3, zero point 0.4 and zero point 0.5. So there is no need to remove the remaining plot. Don't worry, right? Here it's minus 40 dB per decade. From this point, we are going to draw minus 20 dB per decade. Just look at this table where after minus 0.5, you should draw minus 20 dB per decade, right? So how to draw minus 20 dB per decade? From this point, whichever value is coming, let's minus 32. So if it is minus 32, you need to go down by minus 20. So it will be minus 52 and one decade ahead, which is exactly at 5. Hmm? हाँ ठीक है, it's okay, fine. So whatever value is there, you have to go down by minus 20 dB and one decade ahead. So something like this. So it's minus 20 dB per decade, right? So other part is not useful right now. If you want to remove it, you can remove it. If you don't want to remove it, it's okay, fine. The one who is evaluating you, he knows what you are drawing, right? Okay. So what do you think? What is going to happen next? What should I do next? Till now, Bode plot is not completed. We reached here only. So what should I do next? Minus 40 dB from the pole location of minus 1. So I'll go to minus 1, which is here, and again going down by 40, one decade ahead. Yeah, any confusion? Just hmm.
On the y-axis we have 0 to minus 20. So when we are plotting minus 12 on the log paper, so it might not be that accurate. So when we are plotting,
Yeah. So then you need log paper, completely log paper. Then it will help.
no, so we want to calculate where minus, where at point 5, where the graph is intersecting. Like we have taken minus 30.
Point 0.5, you are asking for point 0.5 or x-axis, not y-axis.
So it is
Point
intersecting.
0.5 is fifth line from point 1.
No, that I got. It is intersecting at minus 32 in this case.
Okay. No, no, I don't know. I just wrote what he told.
How we will calculate? How we will calculate accurately?
Okay, accurately.
For my equation.
Then you have to keep this point 0.5 in this transfer function and you have to find out this. If you want to find out accurately, mathematically, you keep omega equal to 0.5, replacing with all j omega. So the way we found out for that this case, what is happening at 0 dB, right?
To replace s by
Point 0.5, right? Right. It's a magnitude plot, so omega will be positive only, right? Okay, sorry, I don't know. He told me and I wrote it. If you are not getting same, then please excuse us. Right. Yes, Nakul. Okay, 1 decade ahead. Yes. So 1 decade that side, right? From here to actually I made a mistake here in drawing. Okay. So Nakul, so from this point 20 40, it's 20 dB down, right? And 1 decade ahead, that is exactly happening at 5, right? So this is 1 decade and this is minus 20. Connecting these 2 points with scale you can draw better. Minus 20. Afterwards you will go to 1 and again you are going to draw plus sorry minus 40 dB per decade. So from this point I am going to be down by minus 40 and 1 decade ahead, maybe somewhere here. Nakul, are you following? Nakul and group, those who are taking care. Then minus 40. So anything, so you have to go down by that much of gain and 1 decade ahead. 1 decade. It's always with respect to 1 decade. 1 decade is easy. You can draw it with octave also if you want, minus 6 dB per octave. That is also same thing. Octave is double. Then you have to go to the next line. Yeah. Anybody has doubt, please ask. This is very important. That's right. Yeah. So look, starting from here. Okay. If you know that your gain is actually starting from minus 12, so you can start from 0 dB from top itself. It's not compulsory. I started from here. 20 log 0.20. We calculated 20 log 0.20. Just give us. Is equal to that was wrong number given by minus 30 was given by him. It was just random. You can calculate it by keeping 0.5 replacing all the omega. That transformation will give you the value. So then it's magnitude. Right? Yes or no? So don't worry, we will draw any order plots before 1.5. Yes. Again, it will follow same way. Okay. There is no 5. Okay, so you are just drawing here. Fine. Then it's minus 20, then minus 40. Just look at the table. So the best way is you to draw the table here itself. Right? start from here, make 0 dB. Yeah, that is what yeah. All when you are driving much yeah, stable is always fine. This is always bond. So although we are drawing here, but similar not happening that side also. Yeah, even more certain something called causal and non-causal. This is always when it's minus causal system. We know what is going to happen. We cannot predict what is going to happen at let's say 10 kilohertz and sitting at 0. We cannot predict that. So it has to be always I'm trying my best. On its signals and system so we are drawing only for causal system. Okay, you studied causal system. So we are drawing only for the causal system. That's why it's always all the minus side, but still it has been drawn at the positive side. Okay. Otherwise, all non-causal systems are unstable. Is there anybody who wants me to come to your desk and ask me? Some people may have doubt that how to find out 1.5. So this plot is not accurate enough, right? So if you want to find out 1.5, one, so let's assume that this is 2. Then between 1 and 2, similar small lines like this will be there, which are actually from between 1 to 2, right? So this is exactly half. The next means 1.5. The half of this value will be 1.5. Yeah. Hmm? Like you cannot make it so much accurately. Unfortunately, that is the problem. When you draw it in computer, we are drawing on actually semi-log paper. Just we want to learn it, how to use the semi-log paper, because like with my experience, I learned that none of your senior have done semi-log paper ever. That's why we are practicing this. Okay, just to become a real engineer.